Greetings, MLTV viewers and participants alike from Dayton, Ohio. My name is Matt Jacobson, and I lead a team of software engineers out of Wright-Patterson Air Force Base in Dayton, Ohio. We work in a research lab, specifically the Air Force Research Lab, and we are building a massive data repository. And as most of you would suspect, this presents a number of unique challenges, not just in the form of the content, but also in the form of the culture around the data, and how we get better at doing our jobs and how we enable better materials discovery and research by inventing new methods and not only relying on tried and true methods for data, knowledge, and information discovery. Back at MarkLogic World 2018, I had established a goal of building a massive data repository, specifically a data hub, leveraging as much of MarkLogic's capabilities as I could. That has really happened with great success for our project. Specifically, we've done it to the tune of about 150 terabytes worth of data, which looks pretty good on paper. And that corpus of data grows every single day. We're marching towards a petabyte and beyond within probably the calendar year, and that's exciting. However, this is not necessarily a great advancement for us because there's not as much discovery as we would like inside of that large volume of data. Well, why is that? We'll get into that a little bit later, but it's been kind of bittersweet. And we inside of the materials community have often said that it's going to take building out a significant repository of data in order to understand what we want to do with it. But that's kind of what I want to focus on today, is how do we recover from a state where we've become very almost overzealous in our collection of data? How do we move to a place where we can do semantic and linked data discovery inside of that enormous volume of data? Not just by promoting new methods of gathering data that rely on things like schemas, but also going back and cleansing, learning, and discovering from old data, because we certainly don't want to lose it. So having said that, my goal really here today is to show what we've learned in the world of schema-driven data generation and discovery, semantics, all of which are relying on the MarkLogic engine behind our toolset, which we call HyperThought. And this all occurs using scalable, reusable tools and methods. And the exciting part is that it also incorporates a significant amount of our community that we partner with, such as major universities, the other defense agencies, and academic institutions, and standards bodies such as NIST, ISO, ASTM, and others. Specifically, what I want to do today is look at creating linked data through both process and data modeling. We'll talk a little bit about what those things mean, the nuts and bolts, and then how we actually use a schema-driven approach inside of MarkLogic. We're going to get into a bit of code and how we can do data and process modeling using those schemas. And ultimately, what we're going to do is take a look at this dreaded word, ontology, how it can be implemented using MarkLogic, and how we create practical touch points for our users that allow, again, them to not just create data better, but also to exchange data better, and ultimately to discover data better. This allows us to empower our research engine, delivering capabilities faster and in a much higher quality. So let's go ahead and dive right in. Findable, accessible, interoperable, and reusable. These are what are known as the FAL Principles. And they've come to very much be a driving set of principles in our organization. And if you take nothing else away from this video today, I would encourage you to remember this acronym, FAIR. Why is it so important? Well, it seems to me that the only reason that we ever capture data, that we exchange data, that we painstakingly define it, and we spend as much time and money as we do on the technology and methods that we invest in is because we have an intent to use the data, either to drive things like business intelligence, or to drive innovation in materials, as is our case, or software, as is the case in so many Silicon Valley tech companies. But ultimately, if we can't find the data, access the data, and interoperate with the data, then we have no reusability. So if you take nothing else away from today's video, I would encourage you to remember FAIR. One of the first things I think that we have to do when we're talking about FAIR from a reuse perspective, being that that is the end state, is reusing the data that we've worked so hard to gather and preserve, is what does success look like? And obviously the presentation today and the demonstrations that I'm going to be doing are very focused on what we do in the materials community. But I think it's applicable regardless of what industry you're part of. We all are familiar with the V's of big data. They haunt us in a variety of different ways. And regardless of the technology that we use, they never go away. And so what you can see here that I've presented is this ball that we like to refer to, this ball of big data points. And this is the linked open data cloud. You can go and look for that on Google if you're interested in learning more about it. But this basically represents, it could be a set of manufacturing activities, it could be a set of promotional events, it could be consumer behaviors or buying patterns, it could be supply chain information. For us, this oftentimes is actually pretty representative of the data points that would be gathered inside of a materials effort. In our community, we are principally concerned with how the processing of materials impacts the microstructure of the material and ultimately how then the material behaves. It all comes down to the microstructure, which all comes from how the material is processed. And as you know, the viewer, the United States military is actively engaged in constantly developing new technology. And so that technology requires us to get smarter and faster. The domain of materials is growing at an exponential rate, such that about 20 years ago, it's estimated that there were around 100 metal alloys that researchers needed to contend with. Today, there are over 1.5 million. So using the tried and true, as I said before, methods of Edisonian experimentation and characterization in materials is simply not sufficient. Needless to say, that ball of data that we're looking at here gets bigger and bigger and bigger and more complex, and there are more interrelations. And it oftentimes feels like we're losing our grip on that data. But what we really want to be able to do is contextualize that data. We want to be able to look at that and not just say, look at the bits and bytes and say, you know, this is an image, this is a data set, this is a data model. Those are all really fine and good things, but what we really want to do is generate knowledge. And that knowledge is in the context of the research that was done. So what we really want to do is be able to adopt the mind of the researcher or the experimentalist who was conducting the experiment, who was doing this activity, to say, why were you pulling on this certain material in this certain way? What was the goal for the research? And how can we take this ball of data that we have in front of us and expand upon it so we don't have to keep going back and reinventing the wheel? So having said that, I alluded to this earlier, if the Edisonian methods don't work, then what does? Well, it's model-driven research. That is, we come up with behavioral, physics-based models for materials that are backed by empirical data. So we need to have this form of validation loop. Of course, that looks good on paper, but what really happens is that the experimentalist and the modeling and simulation expert oftentimes go down two very separate paths, and the two sets of data that they generate really never meet. So that starts to then indicate to us that perhaps we should consider building common identifiers. Maybe we need a lexicon, maybe we need a vocabulary. But what oftentimes happens is, and many of you may have experienced this, you start walking down that road and the next thing you know, you're in an ontology workshop and 2 years later you really haven't gotten anywhere. This can be very, very frustrating, and many organizations ultimately turn around and go a entirely different direction. But I'm here to tell you that I think there's a way that we can recover kind of from that death spiral inside of the schema and ontology space to really get to what we want to get to, and where many of you want to get to, which is backing models. Again, these don't have to be material models. These could be supply chain resiliency models or distribution network optimization models. These could be, again, consumer behaviors in the retail space or in the tech space. But we want to be able to do model-driven research, which means we need really high-quality data. We don't like to talk very often about the dirty little secret of data science, which is that 90% of the work is going to be data cleansing, aggregation, normalization, all for the purposes of preparing some form of an analytic. It doesn't have to be anything advanced in machine learning. It could be a simple statistic that we want to generate. Needless to say, the data need to be clean, they need to be good quality, they need to be schema compliant and conformant. For us, these are some specific scenarios that we walk through, which are things like find me samples that have been made of a certain material or show me figures of merit for this particular part's mechanical performance as it relates to another thing. It's pretty rare in our circles, and probably most circles, to ever want to look for a specific property of a specific thing. More often than not, the most interesting questions are, how does X relate to Y? How does the temperature inside of my furnace, when I'm heating this material or processing this material, how does that affect ultimately its behavior? If I'm going to put it on a car, an automobile, certainly the consumer and the automotive manufacturer care very much how that thermal history dictates the performance of the part. not just from a consumer satisfaction perspective, but also from a liability perspective. And that's a pretty grim part of this that we don't often want to talk about, which is the idea of material forensics. We're all familiar with Boeing's troubles with their aircraft recently. And you better believe that there are a huge number of material scientists who are doing an enormous amount of analysis on the failure points of these aircraft structures to know what caused it. And that goes all the way back to the spot of Earth that the material came out of. But the reason why I have this question mark there is because it's really difficult for us to do that. And this constantly eludes us. And it's not really certain why. They should be easy. And truth be told, inside of a given domain, it may be that a specific expert who's done specific research and has generated specific models and data can give you some of those answers, but that's hardly scalable. What we're looking for, what our end game is to make this something that is enterprise grade, that can be taken all the way to the top of the organization, that's repurposable and isn't dependent on tribal knowledge. So why does this happen? Well, I've selected my top 3 favorites. And we have these 3 blue doors, and behind door number 1 is that we oftentimes are too focused on a single research objective. We oftentimes want to know only how X relates to Y as it impacts a certain set of very specific variables. What happens when we do that is that all the other secondary and tertiary data that's so meaningful and gives us that context is oftentimes not collected. It's lost. Therefore, you may get a research paper that gives you a final decision on what the hypothesis is, whether or not it was confirmed or denied based on the empirical evidence inside the study. But that's about all we can do. We have a report in PDF. We rarely have any of the raw data, and we very rarely have any of the secondary or tertiary data that, again, gives us that important context. What happens in response to this is we often then implement a wide variety of design practices in our software and data that don't really get us where we want to go. And by this, I literally mean down to the interface level. In the materials community, this may shock some of you that we still are contending with SOAP APIs or direct connections through ODBC. REST has not yet become a standard for a lot of organizations. Furthermore, the way that we define data is extremely heterogeneous. How one organization defines a particular metal behavior is likely to be completely different than an organization just down the road. And yes, there are standards organizations, but this is one of the really difficult parts of schema development and data modeling, is how do we take what somebody like ASTM has developed in the form of a data standard and actually implement it. They're going to give you a list of terms and definitions and abbreviations that are acceptable to use. But the reality is if you're the person collecting it, it's very difficult for you to, for example, use Microsoft Excel or Access to gather that data in a way that is consistent and compliant with that schema. So because of this, then we have very little interoperability. And then the organization goes into a complete tizzy, and we have these overcomplicated knee-jerk responses. And as a research organization, I'm here to tell you one of the most frustrating things is that in response to what should be practical, first principle type use cases, a lot of times leadership will tell us to invest in very bleeding edge approaches to doing this, such as using unsupervised learning to try to relearn or to recover the relationships in the data. This is highly impractical. Needless to say, because of these 3 things, this happens on and on and on again. In this death spiral, we don't make any real progress towards FAIR. One little case study to highlight this is that we got a major aerospace OEM on contract. They used a SQL-based solution, which can work if it's done carefully. What was produced was a data volume that was about 10 terabytes in size. And that was the plan from the beginning. That's what it ended up being. And truth be told, they did have their own formal data plan. The problem is that, as I said before, you may have a standard. You may be able to invoke an ISO, an IEEE, or an ASTM standard, but how you actually gather data and exchange data and consume data, if you don't validate those key points, it's very unlikely that invoking a standard is going to be all that meaningful. So what happened to us is that we ended up spending about 3,000 hours of extra effort, $250,000 on scrubbing the data. We worked with actually a number of MarkLogic consulting folks to map this SQL database inside of MarkLogic, which did in fact give us key value pair representations of almost all the data in SQL, but the data model was lost. because of the way that the data was encoded in the SQL structures by the company who developed the software. So here again we have another failure mode, which is proprietary algorithms that take what should be a well-described, well-formed data model, and they break it apart into these unnecessarily complex subcomponents. So what we learn from this is that we can't just use these ad hoc data models. It's not enough just to walk into a room with a contractor and say, yep, that looks good, that'll work, as long as you stick to it. Having a handshake at the end of that meeting is not sufficient. We have to be extremely rigorous about checking the data against the model. And again, the good news is that there are tools for schema validation and for developing triple-based ontologies in MarkLogic that can be deployed in an application stack like HyperThought to ensure that those schemas are complied with. So ultimately, we see this way to break the cycle is the 5 steps that we see here in front of us, which are to model the data, that's building that schema, to capture the data, which means we do need a decent mechanism. And again, Excel is a very common suspect by those who give us data, and it can work. It can work. In some ways, actually, we prefer to receive raw data in Excel instead of in some munged up SQL database. Then ultimately, when you store the data, this gets to that munging problem, is you don't allow the database to break the abstraction of the model. And this is something that's really dawned on me as a longtime SQL practitioner. The practice of normalization, we invented joins to help reconstruct that abstraction of the model. If the complete model has all the things that we care about, for example, for a person, who they work for, what car they drive, where they live, what they're interested in, where they got their degrees, so when we break all that out into our SQL structures, we really ruin the completion of that model, the abstraction of that model. And then the other problem with that is not just that we have to then find ways to reconstruct it, and there are ways to do that in SQL, but it makes it very difficult for us to share that data with other organizations. It's not as simple as somebody calling you up and saying, hey, can you give me the object model for your user type of object? And in our case, it's far more complex than a customer, for example. This is an additive manufacturing build that may have 1,200 properties. So that makes it very difficult. This is, again, those V's of big data are growing every single day, and that makes it very difficult. But as long as we don't break the model when we go to store it, which is ironic and tragic, but it happens all the time, we can then move on to validation. So we can then have regular touch points with those who are generating the data owners, and saying, we can cleanse the data, we can validate the data against the schemas, and we can say things like, hey, we've lost a significant amount of compliance on this particular property based on its data type, based on its range of acceptable values, etc. And then ultimately what we're looking to do is exchange this data in a way that's meaningful. So before I get too far ahead of myself, what I do want to do is cover this idea of a data model, because this does elude a lot of folks, and again, it starts to smell like that nasty ontology word. But it's really not too crazy. What I mean by a data model, of course, is that when you enter a Google search for somebody like Leonardo da Vinci, what you're going to get back is a description of Leonardo da Vinci, but then you're also going to get all those properties. And that's what the Google Knowledge Graph has decided are the salient things about Leonardo da Vinci that you as the data consumer might be interested in. And of course, if you click those links, you'll be taken to URIs that contain important information about Leonardo da Vinci, his associates, where he was born, and you can continue to explore. So without really even knowing it, you're exploring the Google Knowledge Graph. And so that's kind of what we start to define as what linked data looks like. Next to that screenshot of Google, we have what we in our system, HyperThought, have defined as a very, very simple model of what a tensile test might actually be. That is to say that tensile tests contain things like a test frame, they contain things like a sample, they need to have an operator, the test frame has a manufacturer. But what we could do is if we were to serialize this all out, we would get a list of properties that we think are really important that we need to gather. Again, the interesting thing about in our world, and in many worlds, is that the standards already exist. We just need to find a good way to employ them without overburdening the user. Because I want to make certain that I'm not suggesting that we don't chain everybody to their desk and horsewhip them if they fail to comply with our model. That's not at all what I'm saying. There are ways to create touch points, and I'm excited to show you how we've done some of that. And then ultimately what you have there in the bottom right, some of you may be familiar with, is a UML diagram. And that UML diagram was actually provided to us by one of our collaborators. And this is where these design patterns and practices get really, really exciting. Because then we're not just espousing all these great ideas and hoping for the best. What we're doing is working together in an economy of scale to define models. What I'm going to show you a little bit later is a model that was developed by the National Institute of Standards and Technology. And these are folks that we work very closely with on a regular basis. They developed a schema for microscopy. And in a matter of seconds, I was able to put it in MarkLogic and use it in HyperThought to start validating data and gathering data from the microscopes inside of our lab. At least that is what we will be doing with it. That is the goal, to do that. But the starting point is getting those schemas and then having a well-exposed data model, like this one in the lower right, this UML diagram. Knowing what we can expect when we hit a REST API is a huge deal. And again, some of us take this for granted. If you're using a major technology supplier's product, like say Facebook or Epicurious or Marvel or something like that, the REST APIs there are pretty well documented and the data models are pretty well exposed. But for many in the research community, this is simply not the case. It's very difficult, and those schemas and those data models are very closely held. So I'm excited to share with you that a number of these organizations are opening their barriers and letting us have a better perspective on the kind of data that they're building. So what I'd like to do now is actually flip over and talk a little bit about the kind of capture mechanisms that we use inside of our system. Again, it's called HyperThought. It's built on MarkLogic, and it's basically again a large data repository with a lab information management system component built on top that allows us to gather data very quickly from the users, establish context, and ultimately by federating with other systems as well, giving us maximum data discovery. So let's go ahead and take a look at that. So most of us in this industry are pretty well familiar with content management solutions like Google Drive and Dropbox and Box and others. And we've taken a long, hard look at those tool sets. But one of the challenges that we find is that we can't create our own ad hoc data models to attach to the content within those systems. So if, for example, we want to put the keyword payroll, or we want to say payroll year or fiscal year and then attach an integer value to that as a key value pair, that's really difficult to do, at least again in an ad hoc fashion, in a way that allows the users to extend their own models. So what we did in our system is that we created this interface for our lab management tools, and then we added a place where users can create their own files. And then what they can do is they can go in and they can assert to their heart's content any volume of key value pairs of metadata or object linking that they want. So we've selected a folder. Now we're going to click the details button. We have a security model that lets us put in things like distribution level, who can see it, inside or outside the government, export control, etc. And now what we're going to do is we're going to go in and we're going to do something very basic. We're just going to give this folder a topic. And then what we're going to do is give it a value. In this case, investments, because this is one of the briefing charts that I've used to convince my leadership to spend their money on stuff. So this is the investments is an appropriate value as far as this topic goes. Then I'm going to assign myself as the owner of this folder, and this is again a key value pair. It doesn't actually inform who can access it. That's done in a different way. And what you can see what's happening here is we have this selectize, which gives us autocomplete, so I can link to objects. And that's a key point that I want to make, is that we prefer always to link to objects as first-class components of our system rather than just string literal. So in this case, we have our topic of investments, and we have our owner, who is me. And of course, the cool part about this is that with MarkLogic, we don't have to wait. It's instantly available for search and has that universal index applied. So now we can go in and we can go ahead and look for that value. So what we're going to go do is go up to our search bar and look for investment. And sure enough, it should bring up what we're looking for. Again, it's a very fast performance search. There we go. There's our briefing charts. I'm going to click the More button, and we're going to get to see in kind of a card-based fashion what the salient metadata are that we placed on this particular set of briefing charts. And this, again, doesn't seem like that much of an advancement, but again, if you've ever tried to source a piece of technology that lets you create your own custom models, it's fairly difficult, especially at the enterprise level. There are systems, a long time ago I worked with ERP systems that would let you generate up to 5, let's say, custom fields. And there's certainly this idea of creating metadata tags, but that betrays the performance and quality of having a key value pair with things like annotations and units of measurement that drastically impact the repurposability of that data, again in compliance with these FAIR principles. So this was kind of a trivial example. What I want to do now, though, is go in and show you one that's a little bit more complex. And what this is going to do is show how we're not looking for investment anymore. We're looking for something that's more specific to materials, in this case tensile, the tensile properties of a material. There we go. So now we have a significantly higher volume of results coming back from our search engine, again with faceting that's baked into this, which does help some. But the problem that can arise, in spite of the fact that we have things like you can see the logo over there, that icon that shows us what these results are. We have some files. We have this weird arrow symbol. I know what that means, and some people know what that means. But we're not able to really intuit what it is that we're looking at with these results. What we really want to do is be able to go back to that linked data discovery case and try to find data as it relates to other data. So in this case, you can see I do have XML results, and I've got some PNGs, and I do have some Excel files that contain tensile test results, and that's okay. But really what that does for us is it gives us a starting point for a more meaningful search. So we'll talk a little bit now we're going to move over to what that linking the data together actually looks like from the user's perspective. Okay, so now we're back in our Files app. And as is so often the case in any sort of content management solution, what the vast majority of users will do is create deeply nested, complex file directory structures that make sense to them. Perhaps it's by year or by project, or maybe it's year and then project or department or something like that. And then you'll rely on the naming conventions of the files within to give you some meaning. But if I want to know what image I'm looking at, how it relates to a set of test results, I really need to be intimately aware of that file directory structure and those naming conventions. And as I'm sure this won't surprise any of you, there's a very definite half-life on that data. So we oftentimes see people 6 months later who've completely forgotten what they meant when they named a file a certain thing. So what that then implies is that we need not just a data model for our stuff, but we also need a process model for how it all relates. And this is sort of the birth of linked data from our perspective. We don't have a significant enough corpus of data in our system to infer or to generate any sort of meaningful statistic on the occurrence of a certain set of properties. It's so disjointed and heterogeneous that we need the users to do that for us. And the good news is they're kind of already doing that for us. So what we're looking to do is emulate in our system what they're already doing on their whiteboard, maybe on a paper napkin, or if they're really advanced, they're using something like Visio or Lucidchart. So what we want to do is begin giving users the way to graphically represent how they are conducting their work day to day. So what we did is we built this module called Workflow. Again, it's just this long string of JSON structures in MarkLogic that give us these connection points. So you can see we can template things for reuse later. Everything the user does gets saved as a template. So for the sake of simplicity, I'm going to create ourselves a little MLW test workflow. And what we're going to do is what you would do in Microsoft Visio with some key differentiators. We're going to drag these shapes out of our toolbox, which we maintain a pretty simple list of those. A process is anything that can occur really as an event in an organization. So in this case, we've linked them, and now we're going to go in, we're going to organize. We're going to say, well, the first thing we're going to do is we're going to calibrate this machine. We can assign it to a user. We'll leave that blank for now. And then we're going to go in, and we're going to, again, here we see the key value pairs. These are things that we care about as part of this step for calibration. So we may put something in such as the chamber pressure that we want. We want to go ahead and set that up ahead of time. Tell our operator this is what we want to do for our machine to make sure we're right. We're going to go ahead and say that we want this thing at 10 millibars. There we go. So 10 millibars of pressure inside of our chamber. We have room for annotation if we so choose. So in this way, again, just like files, we can extend this out. So we can save this. And again, now the users are able to describe the processes however they want. So now I can go to my downstream process and I can name it whatever I want. In this case, we're actually going to be testing our sample. Yet again, we can type in some notes and or assign a user. But the big thing with this is where the major departure from a normal process modeling tool is that we can start hammering in key value pairs. And again, I want to highlight that the values in these key value pairs, and in some cases the keys themselves, come from a centralized list of managed objects. So now we've got our x coordinate, that's just a string literal. That's not something that's part of any sort of canonical dictionary. And now we're just going to go ahead and give ourselves a value of 3 inches for our x coordinate. And you get the idea here. We can continue to add these things in. And again, because I'm just kind of introducing you to this concept, this is a fairly trivial example. I'll show you a far more complex one here in just a minute. But now we have a flow of steps 1 and 2 of calibrating a machine. Now we're going to test our sample. And we have a full notification system that's built up behind this that lets us assign it to users and execute logically according to what is on the canvas, including one-to-many relationships. So now with this, the key takeaway from this is that now we have those all-important connectors between processes A and B that give us that meaning. As I said before, what I really want to know is the raw data associated with my image. So in this case, I can go and see in step B, if those were images that were gathered, I can then I can traverse that logical link back to that first process and evaluate the metadata inside of that first process. And I can begin to start doing those types of dependent and independent variable analyses that we're so concerned about inside of this space and inside of most spaces. So now what we can do is we can go ahead and open up a workflow that's a lot more complex. So I've gone ahead and jumped ahead here, flash forward the magic of video technology. You can now see this is far more representative of what actually goes on inside of our lab. This may occur over the course of months and months of effort with a dozen different team members. And the key thing I want to highlight here as I kind of scroll down here is you'll see the huge volume of metadata that gets assigned. And again, the exciting part for us is that it's not just values, string literals again, for things like temperature, pressure, etc. You can see all these rich links out to people, to equipment, to files. So we can begin building this sort of a semantic map that lets us, again, follow primary, secondary, tertiary, quaternary type relationships that may be extremely important to us as we do this type of material discovery. All right, so the users are now typing in properties that they care about. Instantly searchable and far more rich than just a metadata tag. We have keys, values, annotations, and units of measurement. And we have not just an object model that's beginning to emerge for a lot of these file types that we're concerned with, but we also now have a process model that links them all together. And this is fantastic, but it's still pretty burdensome. Where we want to go to from here is the idea of having canonical schemas loaded into our system that are preloaded to describe a lot of this. As it turns out, a lot of these first principles have already been established. And as I mentioned, groups like ASTM and ASM and IEEE have already published a lot of this and have been for decades. So now all we have to do is convert it into a usable form of a schema that we can implement in these systems. So now what I'm showing you over here in this IDE is a schema that was provided to us for microscopy from the National Institute of Standards and Technology. Really, really exciting stuff. In all these material labs, and most scientific labs, they have either some form of optical or electron microscope. So this defines how we should use it in the data that we're concerned with. And in addition to caring about what specific properties are coming off of the microscope, what this schema starts to do is also build that process model. So buried within this 1,000 lines or so, the different elements within this microscopy schema are connections to things like the operator, the sample, the calibration settings on the scope. So they published this, they shared it with us, and we've gone ahead and implemented that inside of MarkLogic. So now what I'll do is show you that. We're going to go ahead here and click over. I've got a couple of different tabs open because I want to show you a couple things here, but we're going to go ahead and go over here and we're going to look and we're going to explore. Here you can see the schema has been uploaded And there it is. There's our experimental schema for microscopy, ready to go. And by ready to go, I mean a couple things. One, we can start generating form fields for users to gather data. Two, we can start generating fields for people to programmatically connect with our system. That's one of the key features of our system, is allowing users to access our RESTful API. And a vast majority of our, not a vast majority, a significant amount of our user community does this, connects to us programmatically. So now what I'm doing is I'm actually going to validate a schema by coming in and writing some code. This is all in the MarkLogic help document, so I'm going to run that. And you can see what we've done here is, because this empty sequence is returned, we were successful in uploading this document. So in 15 lines of code, we were able to compare a schema that we had loaded into the system with a file that I generated. This is actually just a dummy example, the one that I'm showing you here. Of course, there is no basic schemas.org, but the URI does. It is a valid structuring of URI. So I was able to come in here and validate that. And if I then go over and look at my results, I can explore now, and I can see there's my valid XML document along with some very simple properties. I figured this would be a little easier to show than that full-on microscopy schema and all the potential issues that you could run into validating data coming into that. And it's worth noting that it's not just an opportunity for us to engage users in the development of these schemas and the sharing of these schemas. This is that exchange perspective. But it's also an opportunity for us to enlist the equipment vendors to say, look, we can make your jobs a whole lot easier. You're going to have customers that will stop picking up the phone and yelling at you about your proprietary formats. You can now comply with this XML schema for generating data off of your scopes and provide automated data ingest into systems like HyperThought, into databases like MarkLogic, and that drastically increases our discovery. So what I wanted to highlight here is not just the communal aspect of developing and sharing schemas, but how easy it really is to use a tool like this to compare and validate the contents of that scheme, the contents of the data that you're uploading to the system against the schema. And as I mentioned earlier, another reason why this matters is, as you can see there inside of that, the node that I've specified, it doesn't have to be something on my local file system that I want to ingest. It can be an existing document inside of MarkLogic. And so this is a really powerful way for us to start to cleanse our data to begin to derive more meaning. So now what we're going to do is take a quick look at the next step even beyond this, which is how we get into controlled vocabularies in the form of a lightweight ontology. Okay, so again, I ask you to bear with me. For some of you, this may be pretty heavy. But here we are again looking at XML in the form of triples that we intend to put inside of MarkLogic to validate data coming into the system, but every bit as importantly, to create quick touch points for users to generate meaningful data. As I said before, what we want them to be doing is not reasserting first principles, but to invoke them based on a known and controlled vocabulary. So in this screenshot here of the turtle file that contains this, what we refer to as Hypergloss, which is our controlled vocabulary that we've implemented in MarkLogic's triple store, is this, you can see reduction of area I've highlighted. That is a scientific principle that we are concerned with. And what's really important in this, where this goes beyond just schemas, is that not only do we have types, we have references back to the classes in things like SCOS, if you're familiar with that, and we also have a definition. This is a significant advancement in creating clarity or reducing ambiguity in what people mean. It wouldn't really be such a big deal if people would come up with their own naming conventions and short codes and abbreviations if they would stick to a common definition. So in this case, you see reduction of area, RA for short. It's entirely possible using an ontology like SCOS to create another candidate term and link it back to this dictionary definition. So we've assembled a couple hundred of these and implemented, as I said, in the form of this thing called Hypergloss. So once we have the content in this form of this set of triples, through MLCP we load it into the MarkLogic triple store, and then what we do is we query it through Sparkle in MarkLogic. Here's an example of the code. This is all the code it takes. It's 19 total lines to retrieve all of those terms and then use a JavaScript library to do autocomplete as the user types these terms in. It's an instant and massive increase in quality of life. I do want to be honest, it's a major work in progress, and one of the things if you're a researcher or somebody who represents a research organization, one of the things that I highly encourage you to do is to go in and begin to evaluate the things that really matter from a properties and data attributes perspective, and enlist the aid of a data modeler or an ontologist. We have one in our lab who generated that ontology called Hypergloss. He was a material scientist converted to a knowledge modeler. That is an essential function to be paired up with any software and data engineering team to make this a practical way forward for data discovery. Okay, great. So we've done some Sparkle, we've got this turtle file, we've got some triples loaded in the triple store. Hooray. Now what do we do with it? Now we actually go in and we punch the data in. So now I'm back in my file manager, and I've picked this data file, this Excel file, and I want to assert some things. There's no metadata, I want to put some metadata on it, so I'm going to click Details. I'm going to add. Now is really where the rubber meets the road on these. Now you can see this list, and as I start to type in tensile, I'm going to look for tensile yield strength because that's contained inside of this file. I didn't have to make it up. I don't have to worry about the definition, because what I can do, as I would type in my value here, what I can do is not just invoke Hypergloss in the key, I can also in my units invoke what's known as QUDT. It's an ontology maintained by NIST and NASA. Super, super cool stuff. As the user types those things, what we can do is we go in and we can show them definitions as they hover over those terms, again, to create more clarity and reduce ambiguity on what we mean. So now we're going to go in and actually look for this. This is a really meaningful search. So now I'm going to look for tensile yield strength, whereas before I was looking just for sort of broad tensile properties. Now I'm looking for something specifically, and again, it's going to come up instantly. And I'm going to see that file. This is what we're looking for. It's driven by, again, a controlled vocabulary that users can contribute to. We do have a process for that. But this is really where we see major advancements happening by doing analysis of the important data, enlisting knowledge modelers to build out those controlled vocabularies implemented in this form. And so then we say, okay, great. So where do we want to go from here? Ultimately, where I want to get to, and I'm going to show you this now, is this type of knowledge search, this type of graph search. So what you're going to see is a force-directed graph. It is beta. I apologize for that funky line there in the middle. But this is a graph, a force-directed knowledge graph constructed from data inside of MarkLogic that reflects important parameters and relationships in the data we care about. Far more meaningful than even just a card-based search. So now I'm going to click on this build. You can see the key value pairs there. It's extremely rich in metadata. Presentation does need a little bit of work. We can do those cosmetic changes. But most importantly, again, from the scientific perspective, so much of what we are concerned with is failure that leads to success. So we need to know what informed the results of our experiment. So in this case, I can go down and I can see the piece of equipment that did my AM build, and there's my calibration file. So now if anything went wrong inside of my build, I can very simply go up to this search type of interface and traverse this knowledge graph. I can down select, I can follow keep relationships inside of this graph that really matter to me. The particular library that we use here allows us to do nearest neighbor and shortest path type of algorithms in the client to allow for maximum data discovery. And this to us is where we need to be going to linked data. So if you've ever kind of wondered, hey, what does this linked data thing look like? This really is what it looks like right here. It is nodes and edges that are connected by meaningful properties. And it's not the edges themselves. When you compare this to what I was showing earlier in that workflow tool, the edges on the workflow tool give us linkage, but they themselves don't have any context or meaning. Where we really start getting to discovery is when we look at these edges between nodes that are meaningful, that are part of a class of either relationship or flow of data or flow of physical item. Now we have context. And so from the perspective of interoperability, and this is a discussion for another MLTV session for sure, this idea of interoperability maturity levels. It's one thing to say that we have bits and bytes that we can share. We would refer to that as technical interoperability. And then as we move up, we get into having sort of syntactic interoperability, which is saying that, well, we do see certain properties that are consistently used between these two different systems. Above that, we can, and what I've got here displayed in front of you is actually this maturity path, and it is a growth path that you have to work through. You can't just jump up all the way to contextual or subjective meaning from these data structures. So where we go then from syntactic interoperability is into semantic interoperability. And we start to understand context, and then we get into contextual interoperability. And from a discovery perspective, this is a very, very serious advancement, because now we can not only understand the what, but we can understand the why, and we can take that and expand our research. So with that, I'm actually going to conclude with some final thoughts. So it's often difficult to neatly wrap a discussion like this with a bow, because of how complex data discovery really is. Anybody who's been involved with it for any length of time understands that it's very much the confluence of a number of different subject matter expertises covering software and data engineering, knowledge modeling, teleology, linguistics, data science, and then the technologies and methods that we use to gather, exchange, and consume data. It is a complex problem, but it's very exciting to see the growth that has occurred across a variety of different industries, and the opportunity for even more growth. So to kind of wrap up my position in all of this, and what I would leave you with, is that making FAIR a core part of your organization will drastically increase the quality of your data, the way in which you approach data, and the way that you acquire both tools and methods to manage that data. Use that reusability in terms of how you intend to leverage, to digest, consume, search for the data, and then let it inform the interoperability. Let it inform the accessibility and findability, and what your strategies are to attack each one of those parts of the FAIR concept. Secondarily, and closely related to that, is this idea of contemplating the data lifecycle. Because of the pace of business, because of deadlines, because of technology limitations, because of culture, we're often far too concerned with how we create the data, and we don't focus enough on how we intend to consume the data. So do take time to think about what the use case is that you're running after, what value you're trying to add to the organization, and then you start linking that back. And I'm certainly not the only one that's proposed this. This is something that others like Gartner and Forrester and a lot of the folks at MarkLogic will talk to you about, is this idea of linking data to business objectives, or in our case, linking data to research, which is our business objective, and the consumers of that research. Furthermore, early and often engaging data and knowledge experts. Oftentimes, we limit ourselves from a subject matter perspective to computer science, computer engineering, and data science. But from a knowledge modeling perspective, from an ontology perspective, there are practitioners. That field is growing, and there are practitioners who are emerging who could add massive value to your teams. I would encourage you to enlist them, as I have, to be able to develop those really rich ontologies. As we saw tonight, the ad hoc metadata attribution is a good thing. Having formal schemas that are used to validate data and create even more touch points is an even better thing. But being able to take it and link it to definitions, to be able to relate it to other key concepts, and to have a canonical vocabulary inside of your system is even better. That is really the way to go in terms of data discovery. So engage those experts early. Then ultimately, don't be afraid to conduct experiments, to run quick, tight iterations, start small, fail fast, and get better each and every time. Which brings me to what's going to happen next for us. As my team is engaging and implementing these technologies and these schemas and ontologies, we're going to be taking a closer look at the Data Hub framework that's been announced, and we're also going to be looking more at entity services to take a more formal approach to implementing what we showed tonight, which was these schemas that we're implementing. But then also to continue growing the schema and ontology efforts. I showed you a microscopy schema. that was supplied to us by NIST. That's really exciting because it's a communal effort. We can enhance it and provide it back to them and continue. I know it may not seem obvious to a lot of you out there, but microscopy is a huge field, as it turns out. Every field in science is huge and has a lot of opportunity to grow these types of data structures. So the schemas will continue to grow, the ontologies will continue to grow. In addition to the fact that like the microscopy schema itself will continue to grow in richness and depth, to cover the scientific domains that we have just in our organization, we would need tens of thousands of these types of schemas. So there's an endless amount of work to be done here. We will continue to do that. And then ultimately publishing that knowledge graph to maximize how users interact with the data. I firmly believe that a knowledge graph driven type of a search experience is more meaningful than just a list or even a card-based search. So that's what's on the docket for us next. I would love to discuss this with any of you in more detail. You should have my contact information through the MLTV site. And I thank you for your time, and we'll see you next time.